we start. Ionic bonds make formula units and salts. All right. The octet rule. Elements tend to gain, lose, or share electrons to acquire a full octet. So n equals 1 consists of 2 electrons because the first energy level only contains 2 electrons, right? So we have 1s2. And then everything else is going to try to acquire a noble gas configuration, which is 8 valence electrons. However, we will see next lecture that sometimes we don't follow the octet rule. Some atoms will get expanded octets or not full octets just because of the way they behave. So in general, we'll use the octet rule, but that definitely can be deviated. All right, electron configurations of ions. So sodium is a 3s1. This is its valence electron. Highest energy level is 3. It loses that and becomes the noble gas configuration of neon. Chlorine, 3p5, nonmetals gain electrons, so it's going to become a 3p6. So always just check on the periodic table, is it a metal or a nonmetal? Metals are going to lose valence electrons to obtain a noble gas configuration, and then nonmetals will gain electrons in order to obtain the noble gas configuration. So it's just showing you there that electrons are gained or lost. Know the location of them. Metals are to the left of the stepladder, nonmetals are to the right of the stepladder. We can also have some polyatomic ions that are involved in this, and the polyatomic ions are typically, they're going to be nonmetals that carry a charge. So you'll almost end up with a covalent bond with an ionic bond, because think of some of your polyatomic ions, CO3 minus 2, SO4 minus 2. Those are covalently bonded molecules, but they carry a charge, so they can also be involved in ionic bonding. So they create this electrostatic bond of pluses and minuses that stick together. We know our charges. So group 1 is going to be all metals. They're going to lose 1 valence electron in order to become a +1 charge. Hydrogen can also be a -1. We will sometimes see that. So if it's a -1 anion, how are you going to name that? How do you name any of your anions? What's Cl-? Chloride. How would you name hydrogen with -1? Hydride. Okay? Group 2 is going to form a +2 charge because it has 2 valence electrons, right? The D block, we can get from +1 to +4, and it is hard to predict. So I'm going to show you a little bit about how we can determine the charges, and we've discussed it briefly. But remember that our transition metals, they will lose their valence shell first. So we don't look at the D block and say that's the valence shell. It's the the S block that comes before it. So if I'm doing 4s and 3d, it loses its 4s2 first, and then it might lose a d. And some of that I'll touch on again, but remember half-filled orbitals are more stable than partially filled orbitals, so we can make some predictions about what the charges are, but it's not always true. In fact, some of them don't have charges. They're not interested in losing. It's just very diverse across the entire board of the transition elements. So the common ones that we'll use, I'll make sure that you understand how that happens. Like, how does lead become a +2 and a +4? So we'll discuss that also. So it's just showing you some of these charges here. Group 5A is -3, and then when you're in 5, you'll notice that you hit the metalloids, and you also have a metal for bismuth there. So you can have varying charges through group 5 because you have all the different types of elements. And then 6A is -2, 7A is -1. Any questions on that? Okay. All right, your D block cations. These elements lose electrons from their highest S sublevel before losing them from their D sublevel. So iron. Go look at it on your periodic table. It may help you to have it right in front of you. So iron is a 4s2, 3d6. So iron will become a +2 and a +3 charge. So let's see how this happens. First thing it's going to lose is its 4s sublevel. So there's 2 electrons here. They leave, and that's how I become an Fe+2. But D6 is a partially filled orbital, and atoms tend to get a lower energy system if they are half filled versus partially filled. So it will lose the 6th and become a 5 electron orbital, and now you've created a +3. Does that make sense? Okay, so go look at tin. What do you think those charges will be? So best thing to do is to write out the noble gas configuration and evaluate which electrons are going to be lost to create the best or the lowest energy system. Is that the configuration for tin? So what do atoms want to do when they lose their electrons? Where do they lose them first? Just in general, where do they lose them? From where? The valence shell. Well, your valence shell is the highest occupied energy level, which is 5. So what do you think your charges are going to be? There's 2 of them. +2, +4. Because this is filled, so it doesn't have a desire to lose any of them from there. So it's going to lose its 2 first from the P, and then lose its S. So +2, +4 are common charges for tin. So some of them you can predict, like take a look at lead. Lead's also going to be a +2, +4. What do you think gallium might be? You might think +1, +3. It's +3. So how do you predict? You just make good guesses. But you'll never have to really come up with charges. They'd have to give you Roman numerals because there's no way for you to actually know. But some of them, you've seen multiple choice questions where it'll ask you what's a possible electron configuration for the Fe +2 or the Fe +3. So you would be able to predict what the configuration is by looking at which electrons should be lost. They're all kind of unpredictable in there. So that's generally how you do it. You just look for losses of valence electrons.
So when does it lose the S before the P?
When does it?
Yeah.
Well, you're just thinking of sublevels.
Yeah.
So sublevels add on. So you have S, P, D, F. So the outermost would be P first, would be lost.
But when it's actually it would take the S before the P.
Always takes from the valence shell first.
Yeah, I know, but like it's when they're the same.
The D is lower.
I know, but the
It'll always take from the outer shell first. You're looking at this example?
yeah.
It'll always take from the outer shell first, and then if there's a partially filled, it's possible, if it's partially filled, that it'll lose from the partially filled to become half filled. That doesn't always happen. Sometimes it even takes an electron from an s orbital and puts it in. So say this was 3d4, it may take it and make it a 4s1 and a 3d4. I mean a 3d5. So there's no rule to this. It's just sometimes they will ask you questions, but they'll make sure that they show you what it is, and you just have to explain the reason why it happened. All right, ionic bonding. We discussed this right before we started. So metals transfer electrons to nonmetals, and the two form bonds due to the electrostatic attractions between them. Or cations, which are your metal ions and anions, form electrostatic bonds based on opposite charges. Cations and anions may be polyatomic. Which are only polyatomic cation? Nelson? Yeah, ammonium. NH4 plus. Yep. All right, so here's how it works. We have sodium. It has its valence electron right here. It's going to lose that valence electron and give it to chlorine. So at that point, it becomes Na+. The chlorine gets an extra electron, hence the negative charge, and then the opposite charges stick them together, electrostatic attraction. So you probably remember that we drew this a little bit. We demonstrated. Sometimes they ask you to draw the formation of this ionic compound. So if you're drawing it using electron dot diagrams, they call them Lewis dot diagrams also, you would draw the single electron and showing that it leaves its valence shell. So when you're drawing your dots are in the valence shell. In other words, the original valence shell that was here is now lost, so I don't draw any dots. I'm not going to put 8 dots now around sodium to show like the new shell has 8. It's just whatever its original shell was, how many electrons now are there afterwards. Well, there's no electrons left in this valence shell after. So I don't draw any dots on sodium, and I just put its charge. Chlorine's valence shell gained its electrons, so all the dots go over there. And you remember if we're doing like more complicated ones like Al2O3, we're going to end up drawing lots of dots and drawing arrows and showing the formations of those, okay? All right, the strength of ionic bonds. Ionic bonds are our strongest type of bond. Well, we'll get to that at intermolecular forces. There are stronger bonds, like diamond is a much stronger bond than a salt. So we'll kind of list them and rank them when we get to that chapter, but right now we're talking about ionic versus covalent. Ionics are really strong. So it requires a lot of energy to melt or vaporize the solids. That's called an endothermic reaction. So if you have to supply energy into a system, that's endothermic, and it requires lots of energy to do this. So for sodium chloride, in order to break this apart, so it's going into the gas phase, delta H, which we'll talk about when we get to thermodynamics, this is your heat energy. And lattice energy is the energy for this bond to form. So what they're showing you is the positive energy for the endothermic reaction means that it's absorbing this. So sodium chloride absorbs this much heat in order to break apart. So if an ionic bond is stronger than sodium chloride, you're going to have a much larger amount of energy needing to be supplied. So we're going to look at individual lattice energies and determine the strength of the bonds. So the way that we're going to determine strength is using Coulomb's law, which again, you don't get this on the AP exam, but you need to be able to utilize it to answer questions. So it's charge and distance, and charge will always take precedence over distance. So when we did this before, we were just talking about a single atom, so we have to kind of divert from what we did before. We were talking about a single atom with a positive nucleus, and we were discussing in the individual atom what was going on for Coulomb's law. Do you remember that? So it was just one atom. Well, now I'm talking about this cation with this anion. So it's going to be a positive charge and anion with a negative charge. I'm talking about this here, the ionic bond. I'm not talking about the sodium atom and the chlorine atom. I'm talking about the bond that forms them together. So charge takes precedence over distance. You need to write that down. So the greater the charge, or the smaller the distance, the more energy is going to be needed to break that ionic solid, which just tells you the strength of the bond. So if I'm asking you about melting points or vaporization, you would determine which one would have the highest based on how strong that force of attraction is within that bond. So stronger bonds are going to have higher melting points. So let's look at these. Which compound has the greatest melting point and why? So part one, lithium fluoride or lithium iodide. So here's what you do. You take your periodic table out and you go and look up first what their charges are, because that's going to take precedence. If they have the same charges, then what do you have to evaluate? Distance. So something that has a smaller distance has a greater force of attraction, therefore it would have a higher melting point. All right, so work through all three of these. I will walk around and try and help you, and then we'll come back and look. All right, so let's take a look. Number one, lithium fluoride has the greatest melting point. The reason why, they're both +1, -1, right? +1, -1, +1, -1. So charge is the same for them. When you take Coulomb's law, don't worry about the pluses and the minuses. Just look at like 1 times 1 is 1. And so when I look at the periodic table, I can see that fluorine, for periodic trends, the smallest atom is going to be helium. So fluorine is much smaller than iodine. Iodine's all the way down, right? So it has lots of energy levels. So it's really like looking at, and you may be asked to draw this as a diagram. So if I'm drawing lithium, look at the size of it. Make yourself a circle. Label it Li, okay? With a little positive on it. You probably want to put the positive charge so that they can recognize that you realize it's a cation. And then you're going to demonstrate where fluorine is. Should fluorine's circle be smaller or larger than lithium? Why? Don't tell me it's because it's to the right. No, fluorine. It has the same, it's in the same energy level.
I thought you were talking about iodine.
Yeah, I know. Effective nuclear charge, right? So it should be smaller. So I'm going to draw a smaller circle here and put F minus in there. All right, so now I'm going to draw lithium again. Obviously, I'm trying to draw this to scale, but I'm not great at that. And then I'm going to draw iodine. And iodine should be much bigger, right? Because it's many more shells in there. So I'm going to draw iodine like this. And I can see that the distance between their nuclei is much greater in Li than it would be in LiF. So this has a stronger force of attraction, right? So it can hold on. Think about it. You can analyze this as your distance between the two nuclei. And so fluoride is much smaller than iodide, therefore greater force of attraction. Questions on that one? And you recognize how to draw these. Okay. Anytime you have to draw a particulate diagram, make sure you're using atomic radii trends and make your circles the appropriate sizes. Second one, Mg, charge on that. +2, chlorine's -1, +2, -2. So don't get yourself wrapped up in how many of these there are. You're just going to analyze charge. Don't worry about the plus minus. So you can say 2 times 1 is 2, 2 times 2 is 4. Therefore, the charge is much greater in MgO, so it has a stronger force of attraction. Okay? Last one, NaF, Mg +2, that's a +1, -1, +2, -1. Greater charges are always more significant than the smaller distance. Okay, the reason why you're analyzing this is because you can look at NaF, and then you can look at Mg and I2, and you can see that this is much larger distance between the two atoms than this one, but charge will take precedence. So you're going to choose the one with charge first. Any questions on that? Yeah.
So when you're justifying, do you say, like, the charge? How would you say?
You can say it just like this. The charge of magnesium is +2, the charge of chlorine is -1, charge is M2, Mg is +2, O is -2. Greater charge, according to Coulomb's law, means greater force of attraction. All right, so this isn't just melting point. I can use this for any words that I want to, like which one would require the most energy to break the bonds, which we just saw in the previous slide was delta H lattice, right? So which one requires the most delta H? You don't know so much about thermodynamics, but you should know anything to break it. What about boiling point? Same thing with boiling point. That's breaking a liquid going into a gas phase. So that's going to require more energy too. So you're just evaluating the strength of the bond and then sort of associating it with other vocab words that you know. Okay, which of the following metal fluorides would have the highest melting point and why? So again, the AP exam likes to give you particulate diagrams to make you figure it out. On your lecture slides, you can't tell because they're black and white. So look up here and evaluate which circle represents which atom. Okay, take a minute to look at it. All right, which is which? So we have our blue circles and our red. What does the red represent? How do you know that represented it? It's the same size in both of these. So whatever the metal fluoride is, the metal is obviously the one that's changing. The fluoride is the same throughout. So these are all your F's in here. All right, what's the next thing that we have to evaluate? Melting point, the first thing we look at is charge. So how do I evaluate charge? You take the ratio. So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So that means that it's in a -1 to a +1 ratio. So now what do? You have to evaluate distance. So the one with the greater distance has less force of attraction, and therefore it would have a lower melting point. So the higher melting point would be the one with the smaller distance. So B would have the higher melting point. The ionic charges are both +1, -1, but the metal cation B has a smaller radius. Good? All right, some properties of ionic solids. They have very strong Coulombic forces of attraction between cations and anions, which means that they have high melting points, they're very hard. Low volatility. Volatility means sort of its ability to just evaporate sitting on the surface. So, like, think of sodium chloride. Does that just evaporate? No. So, it's all of these forces of attraction that keep them in this lattice network. So remember, it's not just like one-to-one. It's an atom surrounded by all these other, an ion surrounded by all these other ions. And so there's something that we don't study anymore, but it was basically would explain to you how the crystal lattice looks. And you could actually figure out, like in the cube of the lattice, if there was one sodium atom, there would be 6 chlorides surrounding it. And for every 6 chlorides, there's 6 sodiums surrounding it. So you can kind of look at the different structures of each of the ionic solids, but they took that off of the curriculum, so we don't learn that anymore. So why are they brittle? Brittle means that they break easily. The reason is because they have this plus-minus structure. And if you try to break it, it will shift and create repulsive forces. So if it shifts and you have 2 pluses, it will break it apart and it'll just cleave it. So this sort of, a little unrelated, but it should make sense to you. If you've ever taken like a really hot dish, they tell you not to put it in icy cold water, right? And it could shatter. So how does that possibly happen? So what happens is your molecules or your atoms at high temperatures are moving very fast, right? So it's holding its shape, but they're all moving really fast together. And when you go to cool it down, if you cool it down too rapidly, immediately those molecules are cooling and they're trying to find their place in their proper network. And sometimes they don't fit back into that proper spot and they shift and they get that repulsive force and they break. So sometimes it's just like being a brittle ionic solid for a piece of glass. Solubility and conductivity. Most are soluble in polar solvents. A polar solvent, right now, because we didn't get to intermolecular forces yet, is water. Water is a polar molecule. You should remember that because electrons are being stored near one end of the molecule compared to another end. We'll talk about it a little bit more today too. They conduct electricity only when molten or dissolved. What does molten mean? Liquid, like melted. So if I take sodium chloride and I melt it, it becomes molten. Or dissolved in a polar solvent as the charged particles are free to move. The higher the concentration of ions in a solution, the higher the electrical conductivity. So this is how it works. You have a water molecule that is polar. So I have H2O. We know from electronegativity already that oxygen is more electronegative than hydrogen. So the electrons are going to pull in this direction, and this becomes slightly negative, and these ends become slightly positive. So water, even though it's not an ionic compound, creates a positive and negative end for itself. So then I put in sodium chloride, and I dump it in, and if the attractive forces between this negative end are stronger for the sodium than the chlorine's negative forces, then it will pull it apart. So that's how things dissolve. So this attraction is greater than this attraction. If it's not, then this doesn't dissolve. So you know that there's some solids that don't dissolve, right? They have greater ionic force of attraction than they do for this ionic polar force of attraction. That's actually called an ion dipole, but we're not there yet. So just ion-ion versus ion-polar is stronger for sodium chloride. So then it takes it and it breaks it apart, which is what we're looking at here. So sodium being with the plus charge has an oxygen molecule here, and your hydrogen's here. You will have to draw this, possibly on the AP exam. I have seen this question multiple times where they ask you to demonstrate how a sample dissolves. So you need to make sure that you put the orientation of the water molecule the correct way. What happens if I flipped it and I put the hydrogens that way? Right? It would be repulsive because the pluses and the pluses aren't going to pull the sodium apart. It's the minus on the oxygen that pulls it apart. So you demonstrate by showing the water molecules surround the sodium, and the chlorides with the negative, the H pluses have that slightly positive charge, and they pull away the chlorine. So you have your sodium, you have your chlorine here, plus, minus, and then water comes in and it orients itself in the proper direction and it starts pulling them apart until this cleaves. So your ion polar, which we're going to call dipole in another chapter, is stronger than ion-ion. It will dissolve. Sorry for being so sloppy. So that's what we're discussing about being soluble. So if the ion dipole is stronger than the ion-ion, samples dissolve. If the ion-ion is stronger than the ion dipole, they don't dissolve. Make sense? Any questions with that? You won't really know until later on in the next section how we can sort of determine that stuff. But right now, just recognize how ionic solids dissolve. So the next thing is conductivity. The more ions you have in a sample, the greater its ability to conduct electricity. So ions conduct electricity if there's like an MgO type thing or MgCl2. There's more ions there. If I take sodium sulfate versus sodium chloride and I put Na2SO4, this is going to dissociate into Na plus, 2 of them, plus SO4 minus 2, 1 of them. This creates 3 ions, whereas NaCl, well, this is like one-way arrow, we can do this, is Na plus plus Cl minus. This creates 2 ions. So which one would conduct more electricity? The one with more ions. That big jug over there of deionized water, does that conduct electricity? Nope. So if you're taking a bath in DI water and you drop a hairdryer in it, you're good to go. If you drop a hairdryer in your bathtub at home, what happens? Why? What's conducting electricity? So your bath water or your faucet water has naturally ions in it. And the more ions there are, the better it is at conducting electricity. But if you use deionized water, hence deionize, it takes out your ions, you would be okay. All right, covalent bonds. When one atom shares one or more pairs of electrons with another atom so that both acquire full octets. This occurs only between your nonmetals. It's a sharing of valence electrons. All right, this chart is going to kind of throw you for a loop. We're going to look at some questions today, but I have not seen any questions on an AP exam that ask you to actually subtract numbers to come up with whether or not it's an ionic bond, a polar covalent bond, or a non-polar covalent bond. But there is a way to actually determine this by looking up numbers. And sometimes it's confusing when you go draw structures and you're determining if it's polar or not polar. You can actually go look up numbers and calculate it. But we're going to do it in theory. We're going to generalize, and we're not going to use numbers, but I'm going to demonstrate to you how that works so that you can sort of see the idea of where polarity will predict what type of bond you have. And just as a general here, the electronegativity difference, where they draw these lines for an ionic bond is somewhere between 3.5 and 1.9. Some people will change their mind here and say, well, I think it's a little bit higher, or I think it's a little bit lower. So these are just general numbers. They're not really set in stone. So a bond's considered to be completely ionic if its electronegativity value is 3.5. You could look up on the chart on a periodic table electronegativity values, and each and every single atom would have an electronegativity value. So if you're coupling Na with Cl, you would take their 2 electronegativity values, you would subtract them, and if it's really close to 3.5, then you would say it's an ionic bond. If you take CH4, and you want to look at that, or CH, I should say, just an individual bond, you would go and see on the periodic table what carbon's electronegativity value is, what hydrogen is, and subtract them. O2. What's O2's value going to be, even though you don't know what it is? 0, because whatever, if it's the same atom, you're going to subtract the same electronegativity value, and you're going to get 0. So notice that a non-polar covalent bond means that there's no pull of electrons in either direction. So polar means a pull of electrons in one direction. So one atom gains most of the electron density closest to it. Whereas nonpolar covalent means that there's an equal sharing of the electron density. So here are your different types of bonds. Polar covalent, you're demonstrating here fluorine is more electronegative, so most of the electrons will spend their time near the fluorine atom. So electron density, and those are the words that they like you to use. Electron density is greatest near the most electronegative atom. And how do we know which one's most electronegative? Because you look on the periodic table and you remind yourself that fluorine is the most electronegative. Electronegativity, remember, is the ability for an atom to attract electrons to it in a bond, not electron affinity. So in a bond, if we're holding hands and I'm more electronegative, I can pull you and your electrons closer to me. So most of the electrons will spend most of the time near fluorine. If it's an F2 molecule, fluorine, F2, diatomic fluorine, it's going to spend equal amount of time because it's the exact same thing. There's no one electron or atom more electronegative than the other. And then ionic would be there is no sharing of them, it's just a complete transfer over. So the words that you're going to be looking to use are polar and nonpolar covalent bonds, and you need to determine it. So sometimes we're going to be looking at just bonds, and then it's so obvious if it's polar or nonpolar because unless the bond is exactly the same atom, it will always be polar, right? Because no matter what, you're going to have two different things. What's going to be tricky is that we have to determine if the molecules are polar or nonpolar. And that's going to come with drawing a structure and then determining overall if it's polar or nonpolar. So this is basically what I wrote. Take a minute and read it to yourself. So if you have partially negative, partially positives, they would be attracted to any of the other ends of molecules. So if you can line up a molecule and this end is slightly positive and this end is slightly negative, then obviously the next molecule that would come in would be organizing itself so that it's attracted. So that's how molecules stick together. All right, let's determine the type of bond. H2, hydrogen. Clearly electronegativity difference is 0. So if you go back and you look at your little chart, it's going to be nonpolar covalent. But realize that you have to do this without numbers. You're just going to look at them and you're going to determine if they're polar covalent, nonpolar covalent, or ionic. Next one, CH, 2.5 to 2.1. What do they consider this to be? But it's really like right on the cusp of becoming polar, isn't it? So CH is one of those harder bonds, but typically you're going to see them, they're going to be in some sort of long chain or they'll be part of something else. But the molecule, the bond itself is considered to be nonpolar covalent. HBr, the difference there is 0.7. We call that polar, yes.
Whenever we do these, they're going to give us a number.
You will never get numbers.
Never.
Nope.
You just have to
Look at them.
look at them.
Yep, and the general rule is if it's not the same, it's going to be polar covalent.
Where are these numbers coming from?
There's actually tables with values on them that you can look them up. I'm just giving them to you. So what you need to know is if I say, is HBr polar or nonpolar, you're going to call it polar covalent. This is hydrobromic acid. So is that polar or nonpolar covalent? It's not the same atom, so it's going to be polar. Okay? This one. So we have CO bonds on both sides. So clearly carbon and oxygen are different. You're going to consider the bond to be polar, but we're going to look at carbon dioxide in a little bit. The overall molecule will become nonpolar because you got the same pull in opposite directions. So make sure that you recognize if something is specifically talking about a bond or if it's talking about an overall molecule. But clearly, these bonds are polar. All right, the next one, LIF, you can measure the values and see that it's ionic based on the 3.0. But what are you going to do to determine that this is ionic? Metal and non-metal, that's it. All right, molecular compounds is when two nonmetals are bonded together to form a compound, and the bonds between the atoms are nonpolar covalent or polar covalent. Polyatomic ions is a combination of nonmetals or metals and nonmetals formed together to form a polyatomic ions. Bonds between atoms are nonpolar covalent and polar covalent or polar covalent. Lewis structures, sometimes called Lewis dot diagrams. This is what we're going to focus on for the next 30 minutes. We only draw Lewis structures for molecules, right? For covalently bonded compounds. They give us a visual representation and the location of the atoms, and eventually we're going to be able to predict the shapes of them and know their bond angles. This is the part that you have to memorize, and it's awful, but it's so doable because it's just flashcarding it. So once you draw your Lewis structures, you can then determine the shape of the molecule and the angles at which each of those bonds are facing each other. So drawing the molecule itself is so important to predicting geometry. So here's how we're going to do it. I'm going to give each of you a note card. You're going to write the rules down because you're going to be drawing molecules for homework. You're going to be drawing molecules for the next 4 lectures every single day. So if you take your note card and you just write out the rules, follow them as you go. You'll just get better at it. You won't need it anymore, but I want you to have them in front of you so that you're not flipping back and forth through all the slides. All right, step 1, you count the total number of valence electrons in the molecule. You literally look on the periodic table and your group number equals valence electrons. So group 1 has 1 valence electron, group 2 has 2. We're doing this mostly for nonmetals because we only are doing it for nonmetals. So phosphorus, for example, is in group 5A, so it has 5 valence electrons. Chlorine is in group 7A, so it has 7 valence electrons. There's 3 of them. 7 times 3 is 21, plus 5 is 26 total valence electrons. So on your note card, you can either write the entire thing you want, or you can just summarize and say total number of valence electrons, or add up total number of valence electrons. Add up total number of valence electrons. Remind yourself that the group number is going to give you your number of valence electrons. So we have 26 in our mind. Oops. I would jot that number down as I was writing my structure, drawing my structure. Second rule, place the least electronegative atom in the center and connect terminal atoms to it with single bonds. So do you remember we use NaSl? It's similar to this, but NaSl doesn't work for everything. Because eventually I'm going to teach you something called formal charge where you can check your structure. I avoided us checking structures in honors and just gave you ones that will work for you. But you will certainly find that there's some that don't work for you. So least electronegative goes in the center. Least electronegative in center. And then attach all your terminal atoms to it. Terminal means the ones that are not in the center. With single bonds. Because obviously they're bonded together. So you stick them all together. All right, the exception to this rule is that hydrogen is always a terminal atom because it only wants ever 2 electrons, so it can never be central, right? Even though it's likely to be the least electronegative in your structure, it's always going to be considered a terminal atom. All right, step 3, complete the octets for all terminal atoms except hydrogen atoms. So what they're showing you here is all the dots, but what we did is we placed the least electronegative in the center, we placed all the chlorines around it, we placed single bonds in between them. All right? So now it says complete all the octets for all terminal atoms except for hydrogens. So this has how many? What does a dash represent? 2, 4, 6, 8. 2, 4, 6, 8. 2, 4, 6, 8. Good? All right, so complete all the octets is your third. Complete all octets for terminals. Obviously, again, except for hydrogen. You should write down all that you need. Step 4, now you add up all of your electrons that you used and you subtract them from the total number of valence electrons that you started with. Any leftover electrons go on the central atom. So I have 2, 4, 6 times 3 of them, 18, 20, 22, 24, but how many did I have? 26. They go on the central atom. Okay? So Step 4, leftover electrons go on central atom. So when you run out of electrons, you're finished. There will be a step 5. We're going to look at it in another example. All right, let's try it again with carbon dioxide, CO2. So again, we count the total number of electrons, valence electrons in the molecule. 4 plus 12 is 16 total valence electrons, right? Step 2, place the least electronegative in the center and your terminal atoms around them and attach them with single bonds. So draw that on your paper. As you're going, you should be drawing carbon in the center attached to each of these oxygens. Yes? All right, step 3 says, complete all octets for terminals. So I'm going to do that. 2, 4, 6, 2, 4, 6. Step 4, any leftover electrons go on the central. So how many did I start with? So I had 16 to start, and I have 2, 4, 6, 8, 10, 12, 14, 16. Do I have any left over? Nope. And what's the problem? Yep. Carbon doesn't have 8, right? So here I am, I've attached. I get here, and we don't have enough electrons. So carbon's octet is not full, so we have to add step 5. So when you do this, and you count up octets, and they're not full, then you start making double bonds or triple bonds. So make multiple bonds to complete the octet of the central atom. So create multiple bonds. To satisfy octets. So we can take from oxygen and create a double bond here, and that will give me 1, 2, 3, 4, 5, 6, and then double here. But I'm still not satisfied, right? So I'm going to have to go again. So I take it from here, and I make another bond there, and now everything is satisfied. So you're always going to fill your octets with doubles or triple bonds. As a general rule, if there's an oxygen in the structure, you always make a double bond to it before making a double bond to anything else. So I'm going to write that here. Always make a double bond to oxygen first, before you go to anything else. If there's a nitrogen perhaps in the structure, you're going to choose oxygen before that. And those are your rules. So for every atom, every molecule that you draw, this will work. Every single time. Sometimes determining, like for example this, you may ask, well, how do I know that this isn't the proper structure? Because that satisfies the rules still, doesn't it? So when we get to the next lecture, I will discuss something with you called formal charge. And we'll actually predict which structure is more likely to occur, either this structure or the actual structure of CO2. So for right now, we're just going to follow our rules in order to draw up the structures. All right, so in some cases, you may have to make a triple bond with your atoms in order to satisfy octets, but you know that. And we know that this one had to be a triple bond because you can't double bond hydrogen, right? If you're making a Lewis structure for a polyatomic ion, you must take the overall charge of the ion into consideration. So when I add these up, iodine is 7, 6 times 3 is 18, and then if you have a negative charge, this means add 1 electron to total valence electrons. If it's positive, what are you going to do? You're going to subtract it from the total number of valence electrons. When you finish drawing your structure, you place it in brackets and you put the charge on the outside. The charge tells whoever's looking at this molecule that you've added an extra electron in. Otherwise, it wouldn't work, right? If we don't bracket it and charge it, someone's going to say, your structure is wrong. You just threw in an extra electron, okay? So always bracket and place the charge around it. Okay, so with the remaining time, we are going to draw molecules. And on the inside, so we just did CO2, we won't do this one. After you draw them, you can open it up and check that you have the correct structure. I believe this is on one of your homeworks.